Hey guys, what's up? I'm gonna do number 9 from the homework here. It is essentially a free response problem dealing with rotation and some kinematics. So I'm gonna do this problem with you step by step, and then I think it'll really help you for tomorrow because the free response I'm gonna give you all tomorrow is going to, or Thursday, is gonna be pretty similar to this one. So let's go ahead and jump right in. We got a solid disk of radius r is 1 meter, is fixed to on a frictionless axis. Several turns of string are wrapped around its circumference, and a block of mass m equals 3 kilograms is hung from the free end of the string. The block is released at rest, various distances d from the floor. The time required for the block to reach the floor is measured in each case. The measurements are shown in the table below. So we got the block here, and we start off with it's 5 meters above the floor, and then we time it, and we lower it to 4 meters, and we release it, time that, and so on. Part A wants us to write an equation which relates d, the distance above the floor, a, acceleration, linear acceleration, and t, time. Then it says put d and t on different sides so that there are no fractions or radicals. All right. Well, really, this is actually a really simple question because what's happening here is the object is falling, right? And if you recall from kinematics, anytime if we had like an object on a cliff and we're falling, we would use our old kinematics equation, which was one of these here, and hopefully you remember that it was that middle one there. I can't highlight it on the screen, but the middle equation, the second one down from the top left, x equals x naught plus v naught t plus 1 half et squared. That's the equation we need because we're looking for how far it falls. Right, that's the distance d. Instead of using an x, we're going to call it d, the distance it falls. Our initial velocity is 0 because it starts from rest. 1 half a is our acceleration, and then we have the t, how long it takes to fall that far. So really, that's the equation there we're going to use to express this relationship. So d is 1 half a t squared, and really that's it. We're just done right there. There's no real manipulation to do. I know it says, sometimes they'll tell you, hey, rearrange the letters so it looks like this. Well, okay, we don't have to in this case, right? We have d on one side, we have t on the other side. There are no fractions, I take it back. There's one fraction, right? Half there. So we get rid of the half. It times 2 both sides. So it's a 2 and a half cancel, and we'll get 2d equals a t squared. All right, there we go. Now we have no fractions or radicals, right? That's the expression, d on one side, t on the other. So we're good. So part B says the graph of d versus t does not yield a line, right? Because obviously, because we have this squared sign here, this will not be linear. It's going to be quadratic. It asks us in the table below to fill in the column headers with the independent and dependent variables that would yield a line whose slope is the acceleration of the block. Then fill in the data points corresponding to this choice of variables. Excuse me. So what we're going to do is, okay, well, it wants us to fill in the table of variables here, and this is important. It says whose slope is the acceleration of the block. Okay, well, acceleration is right there. Acceleration is a, right? So as we write it over here, 2d equals a t squared. Remember that the slope of an object on a graph is rise divided by the run. So if I divide by t squared on both sides, the t squareds cancel, and I get 2d over t squared equals a. So if I were to graph 2d, oops, I didn't mean it right there. If I were to graph 2d as my independent variable, because we're controlling the height, right? We decide how high we release the mass from, so it's independent, right? We depict it, and the time squared, that's dependent. It's dependent upon the height, right? If we were to graph this, right, wouldn't the rise be 2d and the slope would be t squared, which would yield the acceleration of the graph? All right, so that's the case here. So we're just going to plot 2d. All right, so we take our distance from up here back on this graph here, and we're just going to multiply by 2. 5 times 2 is 10. 4 times 2 is 8. 3 times 2 is 6. 2 times 2 is 4. 2 times 1 is 2. And then we're going to take our times from this chart, and we're going to square them. So my calculator here, 2.24 squared is 5.02. 2 squared is 4. 1.73 squared is 2.99. 1.41 squared is 1.99, and then 1 squared is 1. So there we go. Now we have filled in our table, and now we can, part C asks us to plot a graph of the quantities listed in the table. So we're going to plot 2D, and then we're going to plot t squared on this, and then the slope, the rise over the run, just like our expression shows here. The rise divided by the run will equal our acceleration. So let's go ahead and plot those points. We have, looks like we're going to need, each space can be 1 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to start off, and then on the bottom looks like every other space can be 1, 1, 2, 3, 4, and 5. So let's see. The first one is 5 or 10 up, and then 5.02. So just past, probably not even noticeable, just past the 5, right about there. Next one is 8 and 4. It's easy to, we can know exactly where that is, right on the intersection right here. Next one is 6 and 2.99. So 6 and just before the 3, not really even noticeable because it's so close to 3. And then we have 4 and essentially 2, right? Not quite 2, but so close we can't even tell. And then 2 and 1. So right about there. And if you were to get a, I'm going to freehand this, so it's not going to be very good, but you can tell this is pretty close to a line. Well, it's pretty good. Not bad. And the slope should be the acceleration. So we're going to, part D asks us, what is the acceleration of the block as it falls? Well, we know it's the rise over the run, right? It's the slope of this line. So let's just pick 2 points. So let's go ahead and pick 8, 8, 4 as our first point. So change in Y over the change in X. So we're going to have 8, or sorry, not 8. We're going to, let's pick, 8, final for the 8. So we'll choose this point, and we'll choose, how about this point? It doesn't really matter. They're also close to the numbers. 8 and 4, so it's 8 minus 4 on our change in Y, right? The Y values on the side, and then the X values, we are at 4 there and 2, so 4 minus 2. So this is going to be 8 minus 4 is 4, 4 minus 2 is 2. That's going to be 2. So our acceleration is 2 meters per second squared. Then part E says, what is the total rotational inertia of the disk? All right. Well, looking for rotational inertia of the disk, we know that for Newton's second law, the force, net force, equals mass times acceleration. And we're going to replace it with our rotational equivalence. So the net torque equals the rotational inertia times the angular acceleration. We just found the linear acceleration, so we can convert linear acceleration into angular acceleration by dividing by the radius on both sides. So if what the radius says is 1, so then alpha will be the linear acceleration, which is 2, divided by the radius, which is 1. So it's just going to also be 2. And then we're just looking for rotational inertia. We got to find the torque. All right. So rotational inertia, it gives us mass, it gives us radius. We know the acceleration now of the block. So again, Newton's second law, I'm going to use the side of the screen here, equals F equals ma. The forces on the block are the tension force minus the weight of the block. That's going to equal the negative. Remember negative ma here because it's going down. I'm going to tension equals mg plus. Oh, sorry, mg minus ma. And I know all these values now, right? Tension is m is 3, g is 10, minus m is 3, and a is 2. So we have tension equals 30 minus 6. That's going to be 24. So that's my tension. I'm going to plug in the our tension, yeah. And then the torque. Torque. I'm running out of room, so I'm using all available space here. Torque is the force, which is a tension on the. That's the tension right here, right? It's on the pulley or whatever. Times the radius, but the radius is 1, so the torque is also 24. So now I'm going to go down here, and so I'm going to plug in. I'm going to rearrange this for I. I'm trying to find the moment of inertia or rotational inertia. So I divide by alpha, both sides. Alphas cancel here, so I have moment of inertia or rotational inertia equals a torque divided by angular acceleration. And now that I have torque and rotational inertia I equals the torque, which was 24, divided by the angular acceleration, which we just found up here to be 2. So I plug that in, and I find that my rotational inertia will then be 12. So my answer is 12 kilograms times meter squared. And there we go. Not too bad at all. So there's an example of a field response problem where they're giving us data and then asking us to plot a graph and decipher what the slope is and that sort of thing. So you got to rearrange an old kinematics equation and just put it one variable divided by the other one. So that'll be the slope, and we can plot those things. And remember, we can always manipulate, if we need to manipulate our independent and dependent variables, we can totally do that, right? There's no rule that says we can't plot t squared or 1/2 t or 2d or whatever we need to plot. We can plot whatever we want, and then we make a straight line and find the slope, and that gives our acceleration. So yeah, message me on Remind or email me if you have any questions about this problem. Please watch this once tonight at least. That way you'll be ready for tomorrow, because you'll have a fairly similar FRQ for tomorrow. All right, thanks for watching. I'll see you guys tomorrow in class. Have a great day. Bye-bye.